Good morning or afternoon, depends on where you are in the country. Thanks for joining us today. My name is Andy Dio. I'm the Vice President of Marketing for Saratech. And today, our webinar session will focus on optimized design for additive manufacturing. For those of you who joined us on our previous webinar back in June, we talked briefly about the state of the union for additive manufacturing and really covering the technology that exists today in the 3D printing world. So today we're going to talk a little bit more about optimizing design. So with me today, I have a couple of special guests that I'm going to introduce to you in a little bit. But I just want to share with you our workflow for today. So I'm going to talk a little bit about the additive manufacturing landscape. There's a couple updates I want to share with you. And we also will talk about what is the process for design from additive manufacturing. And our two guest speakers will be covering that from the design standpoint and also from the additive manufacturing standpoint. With Solid Thinking, we have Jaideep Bangal, and with Mark Forge, we have Daniel Lazier. And then toward the end, we will have a time for you to enter and ask your questions to the presenters. So a little bit about Saratech. We've been in business in this industry for over a decade. We work with top-notch partners like Solid Thinking, Mark Forge, Siemens, to help our customers optimize their engineering investment and processes. We're located in Mission Viejo, California, but we have presence all across the country. So here's a couple of slides that I want to share with you regarding the 3D printer market. So this is from a study done by Ernst & Young that was released in 2016. They predicted that the 3D printer market will grow tremendously by the year 2020. And if you look at it, it's only 3 short years away. So what does that really mean to you and to our customers in the engineering and manufacturing industry? So if you take a look at from the same report, the application of 3D printing technology in different industries, you see that 3D printing usage within the product development process is growing, and it's only going to get bigger. So as engineers and designers and manufacturers, we have to really take a closer look at how to really leverage this technology to make what we do better. So really, we're talking about rethinking the way that we design things. Right? Typically, when you design a product, you think about strength, you think about how you're going to manufacture it, and how do you optimize for strength and versus cost, and put the best product that you have out there. So today, with our guests, Jaideep Bangal from Solid Thinking and Daniel Lazier from Mark Forge, Jaideep and Daniel is going to talk you through a typical process of how you approach design with additive manufacturing in mind and how to optimize your design for that process. Very lucky to have both of these gentlemen on board today. Excited to share time with you, and thank you both for being here. Before I pass the presentation over to Jaideep and to Daniel, I just want to remind the audience, if you have any questions at all, please type it into your chat box, and we will address your question in the Q&A session. With that, I'm going to pass the presentation over to Jaideep and Daniel.
Hey, thanks, Andy. While Andy is handing over me the presentation, good morning, everyone. Good afternoon and good evening. So as Andy explained a little bit, the 3D printing market, it is growing fast, unbelievably fast than what I was expecting 4 years back. So we will talk about how this market is kind of in line with the designers, design engineers, and then of course we at the end of the day, we have to print it, we have to manufacture it, and that's when Daniel will jump in and give us a quick update on Markforged side. So let's get started on solid thinking. First of all, if you solid thinking is a part of the Altair company. This company is in the business for last 30-40 years, working with almost all the automotive, aerospace, heavy industry, you name it. All the companies use this technology. Now, solid thinking as a company, as a brand, we have different types of simulation tools, starting with the manufacturing solutions, design solutions, to math and systems control solution. Today, we're going to focus on the design part of it. As a design engineer, there are different ways I can design a part. I can start with a napkin sketch, or I can start with the existing part, make that part better, make that part change it, or make it maybe use it for different platform in automotive world, especially we call. Now, so the Inspire is the design concept generation tool we're going to focus on today. The tool itself, it enables designers, engineers, mechanical engineers to come up with the concepts, most efficient concepts early in the design phase. Now, as I was saying, there are two ways to design a part, starting with a napkin sketch, where I know my loads, forces, where I know how that part is assembled to some other part. And in between those 2 points, from forces to support, is my design. And that design, I can go with create one with the trial and error, or I can let the tool figure out how that design can be created. The second option, again, I was saying, was carry over design. Let's say there's design A is being used in one of the components for last 10 years. Again, I want to revisit those, make changes, make it better, make it lightweight, or maybe I just want to use a different material and see what happens, or maybe I want to use different manufacturing process instead of typical casting and machining part. I want to use the 3D printing, take the advantage of 3D printing or technologies we have. The main idea behind the Inspire is to run these concepts, come up with these concepts very quickly, smartly, and most of the time, I would say almost 80% of the time, the new design comes up with a lightweight, lighter than the existing design. That image, that small animation you see on the right-hand side of my screen, is a kind of gives a quick overview about what Inspire does. We'll dive deep into how it really works in a second, but the transparent color part is my starting point, or was my starting point. With the given loads and operating conditions, Inspire came up with that orange or golden color looking part, saying this is how the design should look like. So in a nutshell, given the packaging space, the area where I want to design my part, and operating conditions like forces or pressure, torque, the contacts, or how this part is assembled to some other component, or those are the operating conditions, Inspire quickly comes up with the most efficient design. And it suggests that design depending on the working environment of that particular part. Now, main benefit of Inspire to be used early in the design phase, for me especially, is run 4 or 5 different concepts quickly. If I'm running I'm early in the design phase, I want to come up with 4 or 5 different concepts in very short amount of time, maybe 1 hour. I want to come up with 5 different designs, and then pick 1 or 2 designs which are the best, and then take those to next level of the analysis or designing or trial and error part. But I don't want to wait for 1 week or 2 weeks to come up with 1 design. I want other way. I want 5 designs in 1 hour. That's the main advantage of Inspire to be used early in the design phase. It can solve the challenging problems from topology optimization, topography, gauge optimization. We'll talk about in few more things in a second, but wide range of problems it can work on, from working with a single part as well as big assemblies, large assemblies it can work with. And the most importantly, it can work with existing CAD tools. It's a totally CAD neutral, so you can bring in CAD files directly, like SolidWorks files, directly into Inspire, and at the same time it can export all the CAD neutral file formats back to the CADs. Now let's step back. Let's talk about what is topology optimization. We keep hearing this word for everywhere these days, from social networking to all the emails I'm sure you get in mail, like topology optimization. But how does it really work? So this is a very simple example of our designing a bridge. We learned in the school about designing a bridge, just using two support locations in the either of the end and force on the top, maybe car's weight or vehicle going over the bridge. So that bridge, the design space in this case, the rectangular box is divided into small elements. Of course, in the real world, it's much more complicated than just square blocks. But from that, the Inspire figures out which of these blocks carry loads, which of these blocks are absolutely necessary, and those dark color blocks you see, and this iterative process going back and forth. And this is just one design case where force is going downward. What happens? There are two different cars or something very heavy, or the wind loads sideways. So there are different worst case scenarios can be accounted in the end. So this is how the topology optimization really works. Now, when it comes to additive manufacturing, by the way, let's step back one more time. Topology optimization is being used by industries, aerospace industry or automotive for a long time. Inspire comes with the most organic shape for a component. How nature will design something like imagine the bone. Bone won't be like a straight line. That's how, but it's topology optimization, the organic design. That's exactly what Inspire does in the background. Then we can force Inspire to come up, use some manufacturing constraints. But the design, the organic design is come up with is the best suitable for 3D printing. That's my most efficient design, the lightweight design in this case. But it gives me a freedom to create different, very non-manufacturable geometries, but traditional ways. Put it that way, where I can use 3D printing as additive manufacturing as my manufacturing method. It gives me ability to innovate in different areas. And also I can design a part instead of a big assembly, which will reduce my the problem areas for trace analysis or failures. And the most important is, let's say I'm designing one or two components only, especially working with aerospace or the space components, like the left hand bottom side of my screen. This is actually antenna bracket on a satellite. Only two of those are ever manufactured. You go in the casting way, of course, it's going to take a long time to manufacture, and it's not cost effective. Instead, we go 3D printed way, can be done very quickly, can be analyzed very quickly, and ready to accelerate the product development cycle in that sense. So topology optimization really gives me a freedom of designing a part. Let's take an example of a CAD system. The CAD is basically 2.5D tool, where we sketch something, we extrude, protrude, and do the Boolean operations to create a design. But how about the design? Something like this. Can we design this using a CAD? Possibly, yes. I mean, there are really good CAD users can have a very high skills in surfacing and surface modeling. But what we see on the screen, it can be modeled maybe a days or weeks of time. But what we are saying using Inspire is like, come up with these designs as a very first time as your concept. Model these using some of the very powerful tools within Inspire called polyneuts, the surface modeling, and get it done in a day, less than a day, I would say. Now, going back, another example of the original design was a very simple left bracket on the left hand side of my screen, a typical machined bracket or casting bracket. Then Inspire come up with the best possible design, very organic design, which later can be 3D printed. These are some of the examples I want to show you before I jump into the next set of the quick very short demo of Inspire. Now, taking this topology optimized design to the next level and creates Lattice Optimization. And that's the biggest, I would say, innovation we came up with. Is it's not just take this part and create a lattice structure if you happen to know the lattice, how it works in the background. where we are doing a lattice optimization. So we give a design space and let the tool figure out which areas of that design space need to be a lattice structure and which areas need to be solid depending on the operating conditions and the structural conditions. Just a few other examples about how the topology optimization is being used in the real world scenarios. This is a spring bracket for one of the trucks in automotive world, starting with the biggest design space and Inspire come up with this shape, saying this is where the material needs to be, and the final design is actually for the casting purpose. This is a bike rocker arm, another example of how Inspire is being used today by our customers. I was talking about the lattice optimization. Let's go back to the lattice optimization again and talk about, you can see on my screen, there are some lattice structure and there's some solid, this brown color part. So it's kind of, I would say 20% filled with solid elements. So that's what this particular design needs instead of 100% lattice. If I go 100% lattice, there is a good chance it will fail. So it's not just we're creating a dumb lattice, but this is a very smart way of designing a component at the same time lightweighting the component using lattice structures. But today we're going to focus more on this component is a bell crank for one of the Formula SAE teams race car. They started with the biggest possible design space. I'll show you in a second. That's the focus I'm going to show you today, how Inspire works, so the topology optimization works for this particular component. So the starting point for this part, this design was the existing design from the previous teams that they had. You're looking at the Inspire tool as a GUI. On the top, there are a few icons to work with. There are a few tabs on the top. Very easy to use GUI. If you happen to have using a CAD tool, you can start picking up Inspire within a few hours, just watching few YouTube videos. Our training itself is just in a half-a-day training, so just to get an idea. It's a very easy to understand tool. Now, the very first step when I'm using Inspire or creating a new design is I want to start with the biggest possible design space available for me as a design engineer. And with that, I also want to make sure all this design is clean enough. Now, I exported this part as a shape file, and I can see some of the parts are missing. I can start cleaning up this model within Inspire with just few mouse clicks. Just start patching up or missing surfaces. Look at different areas where I can get rid of this extra imprint in a CAD world where multiple parts join. Or I can also get rid of different manufacturing constraints. In this case, imagine this part was designed for casting. So I want to get rid of all these components or the parts within Inspire. Just few mouse clicks, deleting those components. Now, once I do that, the next step in the workflow, I'm going to call this as my design space. Inspire has a built-in materials library, which we can always create new materials in the library, add new materials or use existing materials, and then we start assigning different loading conditions for our part. Now, the loading conditions is part of our the structural or the setup part of the tab. Now it can be forces. I can define the forces acting on this bell crank. I can also define how this part is connected to some other components, or it can be connected as a fasteners. And Inspire is smart enough to know, just looking at the geometry, where the fasteners can be. Or if it is a joint or like a pin joint, I can quickly define the pin joint between multiple surfaces. If an assembly, Inspire will automatically find out different assemblies for that part. And those pins can be grounded pins or sliding pins. Again, it's smart enough to automatically assign what different connections we have in the assembly. There can be spot welds, contacts, and other features. This particular model takes around 10-15 minutes to run on my laptop. So that's how fast I'm looking at running a new design in Inspire. So this is the same exact model. Also ran this model for multiple load cases. So one load case can be the car just cruising at the speed on a real nice smooth road, or the next one will be is turning at radius or hard braking. So those can be different load case scenarios, worst case scenarios, and then Inspire comes up with a design for those scenarios. The design Inspire basically come up with is that design satisfy all the loading conditions for that particular part, not just one, but all the operating conditions or all the worst case scenarios. And you can see the very first design it came up with is basically hollowed out the part. You put all the material on the outside, added some couple of holes to reduce the material. And if you look at the nature, this is the best possible design anyways, where the material is on the outside, good design for forces, moments, torques, but not necessarily easily manufacturable at that point. And I can go back to Inspire and say, give me a design which is manufacturable by different ways, maybe casting, maybe machined part, or maybe just I want a more lightweight part. And now they Inspire come up with a design which is more manufacturable. In this case, I can take a 1/4 inch plate and mill out those holes or pockets, or this is the injection molded part. I can just find out where the rib structure will be for that particular part. Now, this is the one way. So we have our design. We can quickly run analysis on those parts and find out which design is the best design. But also the next step in the workflow is I want to make sure I want to take this geometry back to the CAD or take it directly to 3D printing. And I can use these polynubs within Inspire and just hover my mouse cursor where Inspire starts creating these polynubs for us. Again, I'm just hovering my mouse cursor and Inspire is creating these polynub structures for us. So final design in this case looks something like that. That's the best possible design, and you can see even this can be 3D printed or it can be sent to manufacturing purpose. And at this point, actually, I will hand it over this design to Daniel to run a quick 3D printing simulation on this part. And if you have any questions, just jot those down or type those questions in the chat window. I'll try to answer it as we go on or at the end of Daniel's presentation. Daniel, you want to go take over?
All right, Daniel, I just made you the presenter. And I see that you're still on mute, so you might want to unmute yourself. So while Daniel's getting oriented and getting his system working, just a quick recap. So what you saw Jaideep did was to take an existing part, use Inspire to optimize, look at several different design requirements, and came up with a solution that was acceptable, based on his requirement. And at this point, he's passing it over to Daniel to take it to the next process, which is to prepare this part and produce it with his Mark Forge printer.
And while Daniel is, setting up his presentation, feel free to ask many questions. Type in the questions there, and then I'll try to answer.
Hey, Daniel, I see that you still on mute. Are you able to unmute yourself?
Sorry about that, guys. Can everyone hear me?
Yes, we can hear you now.
Sorry about that. Yeah, just had a window from GoToWebinar that was preventing me from using the controls, but I think we're all good now. Cool. So thank you very much for that presentation, Jaideep. That was great. Very informative. So as Jaideep mentioned, the main advantage of additive manufacturing or 3D printing up to today has been the fact that complexity and customization don't really cost me anything as a designer. Markforged is looking to take that a step further by empowering it not only to have that flexibility in design and ability to customize, but we're also allowing designers to make parts that are strong as metal overnight and an order of magnitude cheaper than what it would cost to make it through traditional methods like machining. So that's a huge benefit, not only in making end-use parts, but all of a sudden I can make the components that are making my end-use part. So you can have customization on a mass production level, and also have that complexity as well. So with that, just going to give a little background on Markforged and what we do. We're founded out of MIT in 2013. So for this kind of nascent crop of new 3D printing technologies, we're kind of seasoned veterans on that particular landscape. We're at about over 100 employees right now, so growing really quickly. We're based in the Boston, Mass area, again, out of MIT. And we shipped our first printer in 2014, and we've been perfecting that system architecture ever since. Getting a little more into what we specifically do, our solution really involves an end-to-end platform for making these strong as metal 3D printed components. It starts with the software. It's called Eiger. It's a web-based cloud application where you can not only slice your part, but also tune the settings to optimize the part for the specific load cases we're going to see. And I'll get into those features in Eiger that you have and the handles you have to manipulate the parts a little later on. We have a full range of industrial 3D printers as well. Our printers utilize the fused deposition modeling FDM process. What that means is I'm taking a spool of thermoplastic and extruding it through a nozzle to trace layer by layer every little piece, every little slice of my part. So Eiger slices it, and the nozzle is tracing every layer of that, every slice of that end-use part. We also, sorry, I just saw a note that it looks like the slide deck isn't advancing. Is that not the case?
Yeah, we're looking at your not the presentation screen, but actually the I'm not sure if you have a dual screen setup. There you go.
Okay, yeah, I just refreshed it, so maybe that was. I'll just refresh it every time I advance the slide. Sorry about that, and sorry for all the viewers. This is my first presentation on this particular platform, so still working out the kinks. So are we all on the industrial 3D printing platform slide?
Correct.
Great, thank you. So we use this process of extruding a thermoplastic through a nozzle to make our end-use part. We also have a novel method of implementing a continuous fiber through that part as well, and I'll get into that in a later slide. Also worth mentioning, we're releasing a metal 3D printer as well. That's going to have a whole range of other capabilities. I'm going to be focusing on the plastics and composite side, but if people have questions about the metal, I'll be happy to answer those questions after the presentation or over email. And again, where we really shine and set ourselves apart from other additive manufacturing techniques is these components that possess metal properties. So that said, this is a quick stress strain diagram showing both our base plastics and our continuous fibers. So on the left side, and by the way, is everyone seeing these stress strain curves?
Yes.
Great. So on the left side, just like to point out the base plastics that we implement. I mentioned we use a thermoplastic. So the simplest and I would say potentially most versatile base plastic we use is nylon. It's a nylon 6 blend. So that's going to have a really, really low flexural modulus, but in turn, you can get really high wear and high fatigue out of that. So that's often desirable for certain engineering applications, though some engineering applications require more stiffness, which is where Onyx comes in. Onyx is a proprietary blend of both nylon 6 and chopped carbon fiber. So with that, you're going to get flexural stiffness on the order of 40% greater than ABS, which until we came along was kind of the FDM standard for strong 3D printed parts. We take that to the next level, to metal level strength. If you take a look at the right side diagram, we implement a continuous fiber throughout the workpiece, which if you're familiar with traditional layup technologies like fiberglass or carbon fiber, you're familiar with not only the high strength to weight ratio, but also the fantastic performance in both flex and tension as well as compression. So going up the chain of fibers that we offer, so we offer a fiberglass, which is the most cost-effective and versatile material. That's going to be about 6 times stronger than that ABS material. Going up from there, we have a high-strength, high-temperature fiberglass, which is really great for really demanding environments where your part might get really hot or see a lot of wear. So that's going to be great for any temperature environment that's up to 300 C. Going up from there, our flagship material is carbon fiber. In terms of both flex and tension, that's going to be about the same flexural modulus as 6061 T6 aluminum, which unlocks all these applications where not only am I using this for my end use part, but I'm also considering using it for some kind of applications where I'm either doing work holding or I'm doing tooling and fixtures and jigs. So that opens up a lot of capabilities. Worth noting that carbon fiber is also going to have a higher ultimate strength and better fatigue resistance than aluminum. So not only is it cheaper than those aluminum jigs, but it's also going to last longer in an industrial setting. With that, I'm going to get into some of the constraints around not only additive manufacturing, but also our specific technology. So in terms of additive manufacturing in general, any printer that's going to use fused deposition modeling as the base technology is going to have constraints similar to this. These constraints are not necessarily general to all FDM printers, but this is specifically what we need to do to keep parts in that sort of safe zone of design space for our specific technology. So for one, you're going to want to go no lower than 1.6 millimeter wall thickness. A little background on that: as the printer head is tracing each path, you're going to want to make sure that there's 4 total paths, and the nozzle is 4 millimeters in diameter. So you want that to make 4 total passes to ensure that the part is going to print reliably. Beyond that, overhangs are acceptable, which is you know, a pretty vast departure from a technology like injection molding. One thing that you're going to want to do in terms of designing additive is avoid really sharp overhangs. So you don't want to go beyond 45 degrees. If you do, it's not the end of the world. Our technology actually allows you to print support structures. So worth noting that support structures should be avoided on cosmetic surfaces. So that's just one design consideration. Beyond that, embossed details are going to do fine down to 0.5 millimeter. Beyond that, you're going to see some problems with the reliability of those embossed features. Now getting a little bit more into the constraints that are specific to the continuous fiber. For one, in terms of the size of the part, you're going to need 9 total layers. So that's going to vary based on the fiber that you implement, but that's going to be anywhere from 2.5 to 3.5 millimeters total thickness of a section, and that's in the Z direction, or the height off of the print bed. And the reason for that is the continuous fiber is going to need sort of a base and a platform to embed that fiber within, so that it stays in place reliably. Related to that, you're going to need 2.9 millimeter walls. That's going to allow you to make a reinforced loop, so to speak. And if you have any kind of protruding features like this L shape, you're going to need 3.8 millimeter walls, and that's just because you need 2 fiber passes. Now getting specifically into what our technology allows you to do in terms of embedding the continuous fiber. There's 2 main modes, and I'll dive into this with a demo a little later on in the presentation. But in general, there's 2 main modes: concentric and isotropic fill. Concentric essentially traces the perimeter and any internal geometry. So you can see from this sort of sliced section of the view of the part, I have a couple layers of perimeter trace, and I have these internal holes reinforced as well. So situations we're going to be using concentric fill is to strengthen walls and reinforcing those specific features within the part. The big advantage of using concentric over isotropic is you're going to have better control over the fiber usage. So I can say, okay, I want 1 wall, I want 10 walls, I want 50 walls, and that's all going to influence the strength of the part and also the cost of the part, along with how long it's going to take to print. And we'll play around with those variables a little later on when I go through a demo of Eiger. On top of that, the isotropic fill is great for reinforcing flat planes like roofs and floors. And by roofs and floors, I mean the sections of the part that are going to be the top and the bottom. So that's going to be just good practice in terms of reinforcing a part that's going to undergo flex. You can imagine that if I try to provide a bending moment to this part as it's reinforced right now, it's going to be kind of like an I-beam, and that the top section and the bottom section are seeing the greatest stresses. So you're going to be seeing the biggest stress concentrations at the top and the bottom of the part. So it's generally best practice to use what we call sandwich panels and reinforce the part at the top and the bottom. Isotropic is great for reinforcing in every direction. So it's going to be every layer is going to be offset 45 degrees. So it's going to resemble a very similar configuration to a traditional carbon fiber layup. So to that end, it's going to be great for torsional stiffness and resisting any kind of twisting or moment. So with that, let's get into reinforcing this bell crank that Jaideep was kind enough to provide for me as a part to play around with in Eiger. So the blue section here that you see is all of the reinforcement material, all of that continuous carbon fiber. So when I get in and actually look at a slice of this, you can see that this is a really great marriage of the 2 technologies, because the part that Jaideep gave me just has material where the stresses are going to be at their greatest. So when implementing the fiber, especially in this concentric configuration, I'm putting that reinforcement material exactly where those stresses are going to be, so I can actually see, okay, this is going to be, and if I go back and look at the simulation, I can see that this is going to be a great concentration of compressive loads, and there's going to be some tension up on this top section. So this is a really great example of how you would actually go through and reinforce a part so that it's optimized for the load conditions you're going to see. So with that, I'm going to just jump into Eiger. And is everyone seeing the Eiger okay? Is it moving around?
Yep, it's working well.
Great. So as you can see, I've taken this bell crank and I've dropped it in. So what I've done here, and I've just dropped this in and basically flew through the settings of Eiger. I mentioned before there's a few handles you have to turn in Eiger. This is the part you would get if you just said, I want to reinforce with carbon fiber and did nothing else. So you can see we've done essentially the sandwich panel technique, and that's a default setting of Eiger. It's going to take the top layers and the bottom layers and throw fiber in a standard configuration. And let's look at what that standard configuration actually looks like. So jumping into a 2D view, here's what my fiber path looks like. And so you can see it's done 2 concentric rings. So you can see kind of along the outside here, along the walls, there's 2 concentric rings. And it also gave me an isotropic fill. So when we look at what that actually means, I can advance through these layers and actually see that it changes the angle every time. So it's going to be reinforcing against loads coming from different directions every layer. And again, this kind of resembles that traditional carbon fiber layup. Now, going beyond that, if I wanted to tweak any of these settings, I can click this group, and in the 3D view, I can click this group and say, okay, now what I want to do is just do concentric rings, and say we want to bump it up to 5 layers. It's as easy as just dragging those handles around, and it's going to take a moment to just calculate that, and then I save it. And it'll just take a couple seconds here. Great. So I have that part now, and we can go in and look at the 2D view and see that modification I made. So we have these 5 layers here, and we've reinforced that geometry, optimizing more for that kind of directional stress that's going to be seen along each of these sort of, you could think of these like little stress elements or little members. So we've done a good job of reinforcing it to that end. If I wanted to add more reinforcement, it's as simple as going back into the 3D view, clicking and just dragging, and I can say use fiber and create group, and it's going to go ahead and add that fiber for me, and that's going to take a little bit. So I'm going to go ahead and switch to another part, identical part that has been reinforced already. So here's that final part. I've done a few different things with reinforcement. I'll go through each of those. So at the top and bottom of this part, I've gone through and done 12 concentric rings just to absolutely load this part with fiber, make sure that it can stand up to all the stresses that it's going to see in this relatively demanding environment. And I think you'll remember that Jaideep mentioned this is for an SAE formula car. So the loads are going to be pretty significant. So I chose to really bolster this part with a lot of fiber at the top, and then also the bottom of each of these sections. In between, I reinforced the walls with 2 concentric rings. The idea there was just to reduce a little bit of the cost and a little bit of the weight of this part. And then in the middle section, I went ahead and opted for isotropic fiber, just in case there are some strange torsional loads or any other unexpected loading conditions. So that pattern is characteristic for both the top and bottom sections of the part that was hollowed out. So when I look at this in 3D, it's pretty much full of fiber. So you can imagine if you were to machine this part, and if you were to do say a 6061 aluminum, you can imagine that this would be a very challenging part to machine. It would be possible with a 5-axis mill potentially, but it would be very time consuming. You'd have to refixture it in a few different orientations to actually allow the tool to get in there. This process allows you to just click print from here. I can just say print. I can select the printer that I want, and that'll be that. And you can see in the top left here, I always get a very accurate idea of how long it's going to take, how much material I'm using, and what that's going to cost in real numbers. So you can see this is roughly an overnight process, and it's going to cost less than $100, which is a great value for something like this, where you're going to be seeing metal level strength, and you have that ability to manipulate the part to this extent. So again, going back to the presentation, this is what the final part looks like. We actually printed it. It's and it's ready to be implemented on that SAE formula car. Cool. Now I'm gonna actually flip it back over to Andy, and we'll start addressing some questions.
Great, thank you, Daniel. Let me take the presentation back. All right, so just a quick recap on what we saw today. I talked a little bit about where 3D printing is today in terms of product development. It's growing quite a bit and just will continue to grow even more in the near future. And then we saw Jaideep did a presentation on Inspire, a tool that you can use to do optimization for your part, and also selective studies on best case scenarios and find the best solution for what you're trying to do and what your constraints are. And then you saw Daniel did a presentation on the technology that Mark Forge has with the Eiger software that allows him to, kind of design how he wants the part to be supported in terms of fiber. Talked about FDM technology and also, working together. So there's a lot of technology that's happening that's available in the market today. And today we're just talking about two small segments of what's available out there. If you have more questions, we are here to help. We have experts on staff, and we work with excellent companies like Mark Forge and Solid Thinking to help our customer do what's needed, to get their product out the door. So with that, I'm going to move over to the Q&A portion of the webcast. If you have any questions, please go ahead and type them in the chat box. One, I guess it's a comment, and not really a question from Isaac. Isaac was talking about, when he designs and lighter and better part, he kind of have an issue with finding technical specs for performing FEA with the material used for 3D printing. Jaideep or Daniel, do you guys have any comment on that?
Yeah, I can kind of address that, and it's not going to be the most satisfying answer per se, but in general with Markforged technology, if you're just looking at the onyx base material, it is a big challenge because the material is what we call quasi-isotropic, meaning you're going to see isotropy in the XY plane, but the Z layer adhesion is going to be not as strong. in general, some FEA packages will allow you to account for this by setting those material properties. So in general, with both the onyx and the nylon material, you can generally assume a tensile modulus and ultimate tensile strength on the order of 80% of what the full workpiece is going to have. With the continuous fiber reinforcement, it's going to be a little more complicated than that because of the path that fiber is taking. So it may be best in certain cases to model some components of that part independently and apply those loads separately to account for that quasi-isotropy.
And Isaac had a follow-up question. What about Poisson's ratio?
With the Poisson ratio, it's not going to behave quite like
go ahead.
Yeah, sorry, it's not going to behave quite like a metal or even a homogeneous plastic, especially when you look at reinforcing that fiber. When I do it, just because it is such a stiff material, I essentially just crank the Poisson down to 0, and I hesitate to say that's necessarily best practice because it can be a faulty assumption if you are seeing a lot of deflection. But in most cases, the way that the continuous fiber works, it's not going to see very much deflection before failure. So if you are applying strong enough loads to deflect that fiber, chances are you're going to see the ultimate failure point of the part before you see too much Poisson type behavior.
All right, thank you, Daniel. I have another question from Jeff, and I think I can address this. Jeff is asking about whether there's trial software available. I know with Eiger there is trial software available. There's also, for people who are attending this webcast, there is also, we're going to set up a 30-day trial for Inspire if you would like. I know that's really cool technology, and you probably want to take some time to play around with it. And I think Jaideep, will we also be working on some sort of training webinar as well for people who want to take time to try the software?
That is correct. So we'll plan it. There will be, I guess, follow-up email with this trial license as well as this quick overview training in the next couple of weeks.
Excellent. Yeah, just stay tuned. We'll be sending some updates soon. I have another question that came in that asks about will the slides be available? I know our slides will be available. Let me double check with Jaideep and Daniel. I'm sure you guys don't have any problem with sharing a PDF of your deck with the.
I think, yeah, sure. Yeah, I can share the slides. Whoever wants it.
Okay, perfect.
Sure, and I'd be happy to share as well, Andy. We can handle this offline.
Perfect. Again, I apologize for the technical issue that caused us to run a little long, but that's okay. If there's any more questions, we'd be more than happy to stay online to answer. If we didn't get to your questions online here today, we will address them offline. One thing that I would like to ask the audience, when you log off, there is a short 5-question survey that pops up. Please take a couple minutes to answer that. And will help us a lot in terms of content and delivery and what we can do to make things better in future webcasts. With that, I thank everybody for joining us today. Make sure to follow us on social media. All of our webinars and events are recorded and uploaded to our YouTube channel. Go on YouTube, search for Saratech, and subscribe to us, and you'll be notified whenever we have something new up there. Thanks for joining us today, and looking forward to seeing you soon, either in person or virtually. Thanks, everyone.